All right, well, it's my great pleasure to introduce Aleksey, who's visiting us from the University of Texas, Austin this week. Aleksey did his PhD at Columbia University and then has been at various institutes as a postdoc. And I have had the privilege of working with him for several years now, almost exclusively via Zoom. One of my most productive Zoom collaborations ever. So I'm really happy.
This is the first time.
Yeah, we finally got here. We finally have him here in person. He's worked on a really wide variety of topics in his career. So today he's going to focus on something that many of us are passionate about, star formation. But he's also an expert in dynamics of a wide variety of objects, from the galactic center, TDEs, galactic dynamics in general. So if you're interested in any of those topics, I encourage you to sign up to meet with him sometime this week, but don't take up too much of his time because we have a lot that we're trying to get. No, seriously, he's got all week, so lots of time. Please find him. He's in N327. And today he's going to talk to us about something that I'm super excited about, which is where binaries come from. So take it away.
Yeah, so thanks for that very nice introduction. So I'll be talking about the formation of binaries from a simulation perspective. This is work done in collaboration with the authors here, including Caitlin, and is now written up in a Nature Astronomy paper. And then at the end of the talk, I'll discuss some follow-up work that's related to this. Advance. Okay. So I became interested in the problem of binary formation a few years ago, and I was motivated by this question: are binaries captured, or are they forming together? So one of the main ways we think binaries form in a star-forming environment is that you have some gas structure, like a turbulent core or a gas filament, that fragments into a binary, right? That's the scenario that's shown on the left. And there you would get something that could be bound from the beginning. Alternatively, you could take two initially unbound stars and bring them into a bound system via some sort of dissipation. There are many flavors of capture in the literature. One scenario I focused on in this paper was thinking about gas dynamical friction, which is illustrated on the right by these cones. So the idea is you have a gas drag that pulls back on these stars and takes energy from the initially unbound orbit. And in this way, in principle, you could take two initially unbound stars and form a bound system. So this was the question, but why is this interesting, right? So the way that binaries form could have implications for the way the binaries evolve, and also how their planetary systems evolve, right? So if you have, is there an issue? Sorry.
No, we're good.
Okay. And for how their planetary systems evolve, right? So if you have a companion from the onset of the star, right, from when the star forms, that means that the companion is having an influence on the planetary system from the beginning, and any stability limits that you have, any stability constraints that you have, are imposed from early times. Also, if you have something like this, right, you could imagine having something that's quite interesting where you have stars forming at different times coming together, and that could have interesting implications for binary evolution, right? If that did happen, if you had, say, two massive stars that were formed at different times, right, then their evolutionary clocks would be different, and that could look like a interesting evolution for that binary. So how are we going to address this question? So the ideal way would be to look at observations, right? But resolving the earliest stages of fragmentation is difficult. And so it's difficult to address this question observationally. So instead, we turn to detailed simulations of star-forming regions. And in particular, we turn to the existing very detailed Starforge simulations. So these simulations have a lot of physics in them, right? Gravity, MHD, and feedback of various types, from stellar outflows like winds and jets and radiation. So this movie shows an example Starforge simulation, the anvil of creation. So you start with a spherical cloud that collapses into this filamentary structure, and you see stars in white, maybe a little hard to see, forming at nodes, a lot of the times at the intersections of these filaments. This movie is going to go for a few million years. The simulations are run up until the gas is expelled from the system, which is about 10 million years typically. Here I'm just showing the initial few million years evolution. And you also see the nice outflows you have from the stars. Right, so we analyze a few of these simulations. So we focus on clouds that have surface density similar to those of GMCs in the solar neighborhood. So we focus on clouds with masses of 2 × 10⁴ solar masses and initial radius of 10 parsecs. We look at a few different initial magnetic fields and virial parameters, and also one low metallicity cloud. I'm going to focus on one fiducial simulation, but it turns out the main results are not sensitive to choices of parameters like the initial magnetic field and virial parameter. So the first step in our analysis was just to collect multiplicity statistics, right, across time in these simulations. And that's illustrated in these 2 plots here. And this part has already been looked at in the context of Starforge simulations, but this is just to give you an overview of overall multiplicity statistics, right? So the plot on the left shows the fraction of different types of multiples over time, starting with the binaries in blue, and then the higher order multiples in orange and green. And you see that after some dynamical evolutionary times, you settle down to a relatively stable multiplicity fraction. So the binaries are around 12% of all systems, and you have this low fraction because you're dominated by low mass stars. So a lot of the low mass stars are singles, and you see that in the right panel. So this is a bar chart showing the fraction of different systems for different buckets of primary masses. So starting on the left-hand side, you go from the lowest mass where you have a lot of singles shown in blue, and then you progressively get more multiples as you march towards the right, including higher order multiples as you go towards the highest mass systems. A few quick notes. So these are just the raw multiplicity statistics. If you want to compare with observations, you have to think carefully about ranges of separations and ranges of mass ratios and masses in the system. So this wasn't the focus in our work. But just a few quick notes on that for added context. So this is without any cuts on separation or anything. Pretty much all our final binaries fall within this range of a few to a few thousand AU. So we don't have very close binaries due to the influence of softening in the simulation. So gravity within 20 AU is softened within the simulation. And so that prevents you from getting to closer separations. And then this is considering all masses and mass ratios, right? And that can be problematic from both the theory and the observation side. So from the theory side, the brown dwarf mass things, less than 0.1 solar masses, are incomplete in the simulation due to resolution effects. And in the observations, typically you're incomplete beyond mass ratios of 0.1 and down. So you can look, taking cuts in these, at how the multiplicity statistics change. The most notable changes for the higher multiples at high masses, right? So we saw in the previous slide that you had a lot of higher multiples, but at the highest masses, but a lot of those were relatively low mass companions. So if you make this cut with mass ratio, you actually go from something like 70% high mass companions in this simulation to more like 30% for the higher multiplicity companions, triples them.
So you probably said this and I missed it, but is there a lower mass cut in the simulation where you ignore things below a certain, or will it make brown dwarfs and
so there are things that are like, we have things down to the mass resolution limit in principle, which is 10 to the minus 3, but we know that low mass is highly incomplete.
Okay.
But generally, I don't include any cuts in the results I'll present. So let's focus on the initial conditions of the binaries. So this is really the novel aspect of this work, is analyzing the formation of binaries in detail. So I'm going to present 3 different indicators for binary formation, and they're going to paint a cohesive picture as we'll see. So first of all, we can look at the age differences between the binary stars. And that's shown with the cumulative distribution here in the blue. So you could see that the binary stars tend to form at comparable times in the simulation, typically within a few 100,000 years of each other, which is comparable to the free fall time of a gas core. And for comparison, I have this control sample of randomly chosen pairs. And you could see the binaries are much closer, right, than randomly chosen pairs. So this is indicating binaries are forming close together in time. And this is already hinting at an answer to our original question. And it's hinting that binaries are indeed forming together in a correlated way. Another clue comes from the velocity distributions. So that's illustrated here. So these are distributions of angles between velocities. In particular, the blue distribution is the distribution of angles between the velocity vector at the first snapshot the 2 stars exist, so the initial snapshot together. And you could see you have this highly skewed distribution towards the right-hand side, right? And it's far from isotropic. So the velocities are highly correlated for the binary stars initially. And this is also hinting that binaries are forming in a correlated way. And then if you look at the orange distribution, this is the distribution of angles between the relative velocity and separations. And what this is showing is that you have a skew towards the other direction. So the relative velocity is pointing towards the other star. So for example, from the point of view of the primary, you see the other star going towards you. And so this is suggesting that a lot of binaries are forming in the state of radial infall. And so this is also indicating that binaries are forming in a correlated way, and that binary formation is coming from the initial conditions. So the third indicator is looking directly at the binding energy. So this is the most direct check that we do, but it's perhaps not the most straightforward. So why is it not the most straightforward? So it's not the most straightforward because of gas, right? So at early times, the stars themselves are pretty low mass, and their potential is easily dominated by surrounding gas structures. And so if you're looking at binding energies, you have to account for the influence of surrounding gas. And so I'm going to discuss how we do that with an example binary. So first of all, here's just the surface density in a small region of the simulation. So again, you see this filamentary structure with some peaks corresponding to recently formed stars. And you see that explicitly in the right. So the black axis are stars in this region of space. And in particular, this this pair here is a newly formed binary highlighted here, right? And so how do we account for the influence of these gas structures? So basically what we do is for each star, right, we go to nearby gas particles, and for each gas particle, we test whether it's bound to the star plus any previously identified bound gas, right? And so in this way, we can identify structures that are larger than the stars themselves, because we have this non-pairwise method of identifying these bound structures. And I should also say we are going out in order of increasing distance. So we have this basic binding energy criterion, and then we also have a tidal criterion requiring that the tidal force from stars and gas external to this bound structure we're identifying is greater than the internal force times some factor. And we consider a range of factors that's motivated by the fact that from things like the three-body problem, the three-body systems, we know that no one factor will fully capture tidal stability, so we consider a range. So these scatter plots show the structures we identify, which we call halos, around the stars of this example binary. So blue is one star and orange is the other. And the left side shows the minimal halo we identify. In this case, this is our maximal estimate of the halo. And to complete the picture, here is a plot of the velocity structure of the stars in black and the halo in the center of mass frame of this binary in black. So again, you see this radial infall of the two binary stars. And then the colored arrows are showing the velocities of the gas halo particles, where the darker arrows show the minimal estimate and the lighter arrows show the full estimate. And if you continue to trace the binary stars over time, you see this in spiral continue, the radial in spiral continue until they settle into a tight orbit in this case. So that's the basic method. So now we can apply it to all the binary pairs in the simulation. So we now have the distribution of the ratio of potential to kinetic energy for all the pairs throughout time. And the blue is showing what happens when you don't include the effects of gas, right? So if you don't account for gas, then most things would be on the left side of this plot. And so you would erroneously conclude that most are unbound initially. But if you include the gas, as I described, and that picture changes. So then you go towards this orange distribution, where you find that 70 to 80% of binaries are in this bound half, right? To the right of this dashed line separating unbound and bound at this initial snapshot where both the stars are present. And you have this width because of this uncertainty in the halo estimate that I mentioned earlier. So most binaries are bound from birth, but this is a mass-dependent statement. So that's shown here. This is the bound from birth fraction, the fraction of bound pairs in different bins of mass. You could see at the lowest mass end, most are bound from birth, but then you have this decline towards higher masses. And to be specific, this axis corresponds to the maximum of the pair mass of the maximum of the final masses of the two stars, right? And so you have this decline. We attribute this decline with mass due to the influence of dynamical interactions. And one way we diagnose this is through this cumulative distribution of delay times. So this is a delay time from the formation of stars to their first identification in a multiple system of any kind. So you have different bins of the final mass. So the lighter lines correspond to the lowest mass stars. There you go up and you saturate at a relatively low level because many of the low mass stars are never in a multiple, they're in singles. And for the highest mass, right, you also go up quickly and then you saturate to a high level. So pretty much all the high mass stars have a multiple pretty close after formation, but that initial companion is not retained. And so if you look at the full population of binaries, you don't have most being bound from birth. Let's look in more detail at the initial and final conditions of binaries subdivided into this bound and unbound populations. So this is just a separation distribution at the initial time for these pairs, two sets of pairs. So I have blue for the initially bound binaries and orange for unbound. And as you would expect, the initially bound binaries are much closer together with a typical separation of 1,000 AU. And then if you look at the not bound binaries, you have this wider distribution, and it overlaps for the most part with this dash line. So this dash line is the distribution of separations from all stars at their formation time to the closest neighbor, right? So this is the initial condition, but what happens if we advance time? So then we have this shift of the orange distribution inward. So this is looking at the first time the not bound binaries actually become bound in the same system. So by bound, I mean they could be just in the same multiple system without being in the same binary. So they could be companions with, like, one of them could be a companion of a higher order multiple, right? So you have this shift inwards. And then even more interestingly it's even more interesting to look at the distribution at the first time that these not bound binaries actually become binaries. And then you have this jump from this to this, right? So you had them identified as companions, but in a lot of cases not as binaries, right? Because if they were already binaries, then this distribution and this distribution would be the same. So you have this, they were in the same system, and then they became binaries with a much closer separation. And so this is indicative of these stars coming in and replacing some initially closer companion. And to give you a sense of the time scale, right? This all occurs over order 100,000 years from that initial snapshot where both stars are present. There's a range, but this is the median time scale. And then to complete the picture, this is the final conditions of the binaries, the final separation distribution for the two populations. So you end up with a large population at small separations, with a lot of them near the softening scale in the simulation, right? And you no longer have any hint of that initially wider separation for the initially unbound population. And for the bound binaries, a lot you also saw you have an in-spiral towards the final time, right? So a lot of this is driven by gas, and we see this in a few ways. So for example, we see that the orbits also tend to circularize, and we see that a lot of the evolution occurs while the stars are growing and accreting mass. So I've presented some results hinting at exchanges, but it's a bit indirect. And so I wanted to try to get at exchanges in a more direct way. So first of all, I wanted to see what fraction of these not bound binaries have exchanges. And the first thing I did was to look for binaries where one of the stars was in a multiple prior to the formation of that binary. And according to that, you would identify about 65% of this initially unbound population of binaries having an exchange. So that was the initial step. But then I also wanted to do something more visual and see if we're actually capturing true exchanges, right? And not just something like strange with our multiple classification. So I recruited an undergraduate student and a sharer to do some visual inspection of exchange candidates I identified. I built a dashboard for us to visually inspect these exchange candidates. So I pulled out cases where you had a binary that's forming and one of the stars was previously in a multiple. And this is an example of such a case. This will show the binary stars in gray, right? So these are the two binary stars. They're not in a multiple yet. And then any other companions of the stars are shown in red. And this is probably not super useful here. This is just an absolute scale view of this interaction. So the axis ranges are fixed, and here the difference is it's just scaled to the binary separation. So it's easier to see things as things get closer. So I'll play this stepping through. Now, like what we're looking for is the two stars coming together and the other companion going out and being kicked out. We won't see, very smooth evolution given the time cadence of these simulations. So we only have snapshots every 20,000 years or so. So you could see from the range, the two stars getting closer, and then that companion is kicked out. You're left with a binary. Actually, here it's embedded in a larger quadrupole system. Right, and so doing those inspections for the exchange candidates I identified gave us confidence in that identification. So indeed, it does seem you have a lot of these exchange interactions. So another consequence of exchanges and dynamical interactions is that you can destroy some of the binaries that you form, right? So not all of the binaries that you form will stay in the simulation. So that's illustrated in this flow chart here. So we have about 1,900 binaries formed in our fiducial simulations. So this is from stacking 3 simulations of clouds with the same initial parameters, just for better statistics. Most of them are forming bound. And then if you follow the evolution, you find that about half survive, meaning that the two stars remain in the same multiple system, either as a binary or as part of a higher multiple, right? Here, the binary stars are in blue and the other companions are in orange. And on the top, you have the non-surviving branch. So here, at least one of the binary stars is split off into a single, right? And this splitting has interesting consequences. For example, for the mass function of single stars, and that's illustrated here. So this is a bit of a busy plot, so bear with me. So these are all mass functions, right? The gray is the mass function for all stars, so that's really the mass function. And then I have different subpopulations of single stars. So the blue is all singles, right? So you have the steeper fall off, as you would expect. You have more single stars towards lower masses. And then I have singles from multiples, right? That's the green for singles from binaries. And you could see you have this flatter slope that corresponds well to the overall mass function. Whereas with the things that were always single, you have this steeper fall off. So these these singles that were in binary stars have this flatter mass function, and this influences the overall mass function of single stars. So there's some imprint of the presence in a binary into the mass function of the single stars. So this isn't the end, but this is a good point to sum up. So these are mostly results in our paper. I want to summarize this part and then pause for questions. So I've described how most low mass binaries are bound in detailed simulations of star-forming clusters. Captures subdominant for binary formation. This conclusion is robust to variations in initial magnetic field, virial parameter, and metallicity. So we have the same fraction of binaries bound from birth in simulations where we vary these parameters. And as I've alluded to, or tried to allude to throughout the talk, this bound from birth origin of binaries has implications for binary evolution and for the planets that are hosted in binary systems. So you can have influence from the companion from early times for planets in binary systems, and perhaps less obviously for singles that were in binaries, right? You can have influence during that binary phase before the single was kicked out. And so even single stars could have this imprint of binary companions on their planetary system. So I'll pause here for questions and then continue to describe some follow-up work.
Is the decline in the mass function you just showed in the previous slide to the low end a real in terms of your simulations, or is there any?
Great question. I wouldn't trust the mass function at low masses.
There's a question from online audience. Oh,
Can the simulations tell you anything about the mass ratio distributions?
Yes, so that was looked at in a previous paper that I cited, David Gusinoff. So there's quite a lot of relatively low mass ratio binaries that are forming, like around 0.2 mass ratio. I think it's more skewed towards low mass ratios compared to the observations. And one possible explanation is that so these simulations don't have disks, right? And so you're missing things like disk fragmentation, which could account for higher mass ratio binaries.
May I?
yes. Please.
So a question about triples. I liked your diagram of the relative angle between velocities and radius vector. Did you look at the triples and the mutual inclination between the orbits? Because you might have quite a large number of these triples.
Yeah, so I did at some point, but I actually don't recall I think there was like we wanted to be sure we understood like effects of softening before analyzing too much details of triples. So it's not like it's something I looked at. I think there was some alignment between the orbits, but I can't recall for sure.
Here's a quick question. What was the resolution of our simulation? Is it called?
So the mass resolution was 10 to the minus 3. And then we had this softening that I mentioned, which at least for the sinks, so the star particles was of order 20 AU. Yeah, but for the gas, it can be like much larger actually, softening.
So you mentioned that to very low mass and you wouldn't trust it.
Yeah.
But then is that the flatter part of that green curve for the from binary, singles from binary, so that's not significant at all?
I wouldn't, no, I wouldn't ascribe to
Because these days, even observationally, you know that we go pretty low mass for the IMF studies. You Austin, that there's Matthew DeFrio's study, for instance.
Yeah.
So it could be tested. I mean, for that very low mass. So it would be really nice too if we could actually test that area.
Right, yeah, maybe in the future. Okay, any further questions before I continue? Okay, so I'll get started on the last part of the talk. So one of the follow-up projects was testing what effect softening has in the simulation, trying to see how that influences our results quantitatively. So I've started to look at this again with my student, Anna. And our initial steps were to look at this in a very idealized way, right? Just for simplicity, we're starting with some idealized system, right? So this isn't tied to StarForge in any way. We're just looking at 3 body encounters in Newtonian and softened gravity and comparing the results. So this diagram illustrates our basic setup, right? So we have all equal mass stars, circular binary, and then a tertiary that's coming in on an eccentric orbit. And then we're starting with the 2 stars that are just outside the softening length. So initially, we have the same initial condition in Newtonian and softened gravity, and we don't have the stars feeling softening, but as the star comes in and you have a chaotic interaction, these stars will start to feel this gravitational softening. This is an example integration. So I had her do integrations with randomized phases and inclination angles for softened and Newtonian gravity. So this movie shows the single and the binary, and it's integrated in all cases to the point where you have dissolution to a single star and a binary. And this is pretty much the mathematically guaranteed outcome in this type of setup. So these show the distributions of outcomes that we've gotten so far. So this is the final 7 major axis distribution of the surviving binary, and this is the final eccentricity distribution. And here, there's both the PDF with solid lines and the cumulative distributions with dashed lines. And recall that the initial 7 major axis was 1 in the setup. So there is some effect of softening in these distributions, but so it's surprisingly mild, I would say. And so this is something we're still trying to understand. But if this holds, this is actually encouraging for our interpretation of the simulations. It's indicating that the softening isn't completely going to throw the dynamical encounters off from what they should be. And so maybe like at least qualitatively, what we infer from dynamical interactions in the simulations is reasonable. Yeah, so this is the results so far, and we're going to investigate exactly why the softening is so mild. The other follow-up work I'm looking at is to look in more detail at these gas structures around stars and how they relate to the reservoir of mass that accretes onto different stars. So I'll describe a lot of qualitative results and show some example visualizations of gas around a newly forming star, just so you can see a lot of the rich dynamical behavior that goes on with the gas at early times, like the effects of outflow and cycling of gas all around. So this is a newly forming star. This is starting at the first snapshot it exists, and the colors show the surface density around the star, and this is always in the star frame, so it's always going to be at the origin. And I'm going to play the movie and just look at what happens with the gas. So it's not the highest resolution movie, especially on Zoom. So I have a it's a bit clearer on my screen. But right, so you see some outflows, and then you'll also see clumps coming in, right? So this star is actually it ends up being 0.6 solar masses, and it's never identified persistently in any sort of multiple system, but you still have an encounter with a gas clump there that you'll see in the next few slides corresponds to a stellar encounter, and then you have a lot of very dynamic movement at late times. So from that already, you can see there's a lot of dynamism in the gas structure around stars. And to illustrate that further, I'm going to show you what happens to halo around this star. So this is the halo that's identified at the initial snapshot, a bit downsampled to avoid overwhelming you with arrows, and the white arrows correspond to things that will accrete onto the star. And I'm just going to continue to follow this same set of particles over time. So it's not the halo at different times, it's the initial halo over time. And you'll see that you start with this nice sort of organized structure we identify as bound, but you'll see very quickly that gets messed up and scattered very quickly due to the effects of feedback from this star. And you have another star coming in. So the X's in this movie are stars. Their size is logarithmically related to the mass. The orange circles are crude estimate of boundary radius around each star. And so you like this view is a bit tight, a bit small range, but you could see like quite a lot of dynamism going on, and this initial halo is scattered, and at the end you have this outflow, flow of gas and towards the top right. So that is nice, but it's a bit hard to see the bigger picture from that small scale visualization. So I also have this movie showing that same set of particles in the inertial frame. So that's shown here.
So what is the time scale from the beginning to the end?
That's a good question. So it's 30s, maybe half a million years. I'd have to double check. So again, you see the outflows coming from this. Sorry.
Did you say 500,000 years between frames?
Not between frames.
From the beginning to the end. Yeah, whole, yeah.
Yeah, between frames it should be 25,000, and they're around 30 frames. And so I don't know if you saw it, but actually a lot of the gas in this case went to this other star. Yeah, and so this illustrates a few points. One is that not all of this gas near the star will accrete onto it, and another thing is that not all of the gas that accretes onto a particular star starts near it. So you had this thief star that took a lot of this gas, a lot of these gas tracers, and some of this, a lot of this dynamics is reflected in this comparison of this halo mass to the final stellar mass that I show here as a function of the final stellar mass. So this corresponds to our maximal estimate of the gas halo. And so first of all, you see that typically you have a more massive halo than the final star, which you would expect given the effects of feedback. But there's this huge scatter, right? So there's not a straightforward one-to-one relationship between the mass of this gas structure and the mass of the final star you form, right? Like that's not surprising given all the complicated dynamics we just saw. You also see some cases where this halo is less than the final stellar mass. So how can that be? So there are a few ways that can happen. So one is we're looking at a halo around each individual star. So if we're looking for a halo, it has to be tied to the one star, and this can be problematic for stars in denser environments or stars in multiples where you could have potentially accretion from a common halo around multiple stars. So we can mitigate that somewhat by repeating our analysis, looking for halos, but this time looking for them around binary stars. So instead of looking star by star, we take the binaries we identified and combine them to a single particle and then repeat the procedure for that combined binary. And so this shows the comparison when we include those binary halos. So the total mass of things in either the individual halo of the star or in a binary halo if it has a companion. And that mitigates somewhat these lower outlier points, but particularly at higher masses, you have this population with this ratio below 1. And a lot of that comes back to this cycling of gas. So a lot of the gas that ends up accreting onto the massive star doesn't start near them. It can start from far away and then come towards them. And we saw an example of that in the visualization of these tracers, with the yellow tracers coming towards that other star. And this is not surprising if we look at the time scales also of accretion onto the most massive stars. So that's shown with the scatter plot. So this is the time scale for a star to reach 90% of its final mass as a function of that final mass. So there's a huge amount of scatter in this time scale, but generally you have this upward trend where the most massive stars can take of order 1 million years to accrete this mass. And so they're accreting for longer, they can accrete from much larger spatial scales. And so this brings me to a final summary, a slide for this part. So, and I'll end here and take questions. So final observations on these gas structures, right? So we've been looking at bound gas structures near stars at early times, right? And looking for seeing if there's a relationship between the mass of the structure and the final mass of the star. And we see there's no simple relationship. And this type of thing has been noted before by other groups working in theoretical simulations, but we're using different ways of identifying gas structures. We see typically more massive halo than the final stellar mass due to the effects of feedback in the simulation. But at the same time, you have a huge scatter, right? Like you have this lot of dynamics going on. And also you can have, especially for the most massive stars, the halo near the star at early times doesn't reflect the full reservoir that's going to accrete onto the star. And so you can have halos that are smaller than the star ends up, and you have the cycling of material near the star. And with that, I'll stop and take any further questions.
Can you go back to the slide from the softening section with the PDFs?
You'll have to stop this one.
Yeah. So The eccentricity distribution, what is going on at the eccentricity distribution?
So that's a good question.
So Nestle and then back the other, but.
So we have to check this in detail. I have an idea for what it can be. So if the softened force has a break around half the softening length, I think. And so that might be reflective of that, but I would need to double check. Yeah, it's still very much in progress.
Okay, so it's numerical, this is not real.
Well, so I mean, all of it is numerical, right? The point is to test. The point is to test this particular numerical softening, right? And like maybe this reflects a particular feature of that.
Sure.
Yeah.
I'm curious about the outflow simulations you have in that huge cluster. So can you see a trend that some of the mass is going from particular system to more other systems? For example, like the halo from a more massive protostar is likely go to the smaller ones, or it doesn't depend on the stellar mass of the central object. It's just depending on the density in that cluster.
Yeah. So you're asking if the mass that goes into a massive star comes from lower mass.
Yeah. Or vice versa.
So it's not something I've checked in detail, but I think it must be that the higher mass stars are drawing from the lower mass case, just like by budget, right? Like to accumulate all the mass that they have, you have to draw from a larger scales, and that would include structures that would have been near other lower mass stars. In that example movie I had with the outflow, so the final mass of that original star was 0.6, and then a lot of that mass went into what became a 5 solar mass star, actually.
Yeah, so what is your best resolution for that movie that I'm just following up with that? So I'm wondering how much of the gas actually end up actually in the other system, stellar system, or they're just passing by?
So there were a few ones. So I was checking this recently. Where is it? Yeah. So I think most of the mass, I have to refresh. Yeah, so most of the mass, I think, ends up like of the things that accrete from this structure, I think the largest quantity ends up in this particular star. Yeah.
And is that the most massive one?
Oh, well, I don't know if it's the most massive one. The final mass is, I think, 5 solar masses. Like initially, it's not the most massive. Like
But it became massive later.
Yeah. But you have other, like the sizes are like logarithmically related to the mass in this movie.
Thank you.
Other questions in the room or from our online audience? Yeah, go ahead.
What is the typical age difference in the stars and the binaries?
Yeah, that was, well, it's a bit hard to see with the scale. It's a few 100,000 years. Yeah, so this was this distribution here.
How do you define the age of the stars?
Oh, that's a good question. So it's just the first appearance, the first time that sync is in the simulation.
Even if the stars are formed, it is still accreting the masses from the halos.
Right. Yeah. It's its first appearance, not like when it reaches the final mass. I mean, accretion, as we saw, can be quite long for the most massive stars.
Could you remind me? I just can't remember the mass range of these, you low mass binaries, but what did you define as low mass?
Oh, I didn't, so that's a good question.
Yeah.
Yeah, just based on this plot, right? So above a few solar masses, you have this.
And you go all the way down to minus 0.5.
Yeah. Anything else?
We have no other questions. Let's thank our speaker again. Our speaker will stay with us this week. And if you have any further discussions you want to have, please sign up and to meet with our speaker. And we will have another special origin seminar on this Wednesday and from 11 to 12, because one of our hosts has other activities afterwards. And also at this.
Be here.
Yeah.
And if anyone's interested in joining us for an informal lunch, we'll be leaving, let's say, meet in the lobby in around 5 to 10 minutes.
And the sign up sheet, yeah, link is in the email.
Yeah, that's right. Right.
Thanks.